Okay, so I was told that today you finished talking about cylindrical shells in the lecture. So what we'll do today in the lab is to consider some examples on how to set up integrals to give the volume of certain solids of revolution using the cylindrical shell method. I will utilize the same examples as we had last time. I mean, those coming from worksheet number 3, which we solved using the disk or the washer method last Wednesday. But today we'll set up the integrals using cylindrical shells, right? And then I see that a couple of you submitted some questions on the chat. Yes, after this examples, I'll go over those questions that you have. I see Jocelyn's question. That's a nice one. And then Lucas, can you send me a screenshot of problem number 10? Because I don't have a copy right now of the written homework, but I'll go over them towards the end of the session. I just want to start with some quick examples for the cylindrical shells method because at least Jocelyn's question is about the volume. Um, and I guess it would be helpful if we go through first some specific easy examples to give you a brief idea so that along the way you can think about the solution to your question. But we'll address that towards the end of the session. Okay. Now, just a quick review. We are using integrals in order to get the volume of certain solids of revolution. Last time we talked about the disk or the washer method. But essentially, these formulas for the volume are derived by imagining the solids to be formed by a stack of cross sections or two-dimensional cross sections. But for cylinders, it would be three-dimensional shells. But anyway, so they are formed by some cross sections. So that's why we are integrating some sort of an area formula with respect to, say, some variable. Let's say I'm integrating with respect to the variable x, and then the integrand always is some sort of an area. Well, we saw that whenever using disk or the washer method, okay, if I have a generic region like this, from A to B, right? And my shaded region is like this, okay? And then my AOR says the x-axis. So basically, we were choosing the strips to be perpendicular to the axis of revolution. And I will tell you in a moment why we do so. So since the AOR here is horizontal, I'll pick vertical strips. Vertical strips always go with the variable x. Then so the bounds for the integral would be the bounds for x. You see that? And then imagine what happens to the vertical strip when I do the revolution. When you revolve that strip, or you can think about the entire region with respect to the AOR, then the cross section that you will produce would be circles. Okay, and that's why for the method of disks, what happens is that the area is replaced by the formula for the area of a circle, pi radius squared dx. Okay, and this radius r should be a function of x. And we saw last time that that is nothing more but the height of the vertical strip, right? The radius is the height of the vertical strip. Whenever measuring the length of vertical strips, we do top minus bottom, all right? Now, for the method of washers, okay, you consider, suppose we have this region, but this time revolve around this axis of revolution, okay? By that, okay. All right, and then again, you use vertical strips, okay? And then imagine what happens when you do the revolution with respect to that axis axis. Well, what happens is we get a big circle as our cross section, but there is a hollow over here because that portion corresponds to empty space because it is not part of the shaded region. So basically the cross sections here would be a punctured circle or a circle with a hole in the middle, right? So basically what we do to find the area of this cross-sectional washers, right? We do the area of the big circle, pi capital R squared, and then, but that will give us the area of the entire circle, right? But remember, this circle has a hole in it. So basically there's a hole here. So the area should not be computed using that big radius alone, but we need to subtract from it the area of the smaller circle because that represents a hollow. So that means we need to subtract the area of the smaller circle. Suppose that smaller circle has radius little r. So that means our cross sections has net area pi r squared minus pi little r squared. And that's why, if you remember, for the method of washers, our integrand looks like pi times outer radius squared minus inner radius squared. All right. And I hope you you are now proficient in setting up integrals using the method of disks or washers, right? Now we'll focus more on the use of cylindrical shells. Cylindrical. You know, it's Friday when my handwriting is very messy. Okay, cylindrical shells. So basically here, suppose I have this shaded region. Okay, over here. And I want to revolve it around, say, the y-axis. Okay. Now, for the cylindrical shell method, this requires strips to be parallel to the AOR. The double bar here represents parallelism. So here the strip should be parallel to the AOR. So in this example, my axis of revolution is vertical. So I need to use vertical strips. And again, whenever doing vertical strips, your integral will be an integral with respect to x. Okay, that's always the case. And then since we are integrating with respect to x, the bounds here will be bounds for x. So suppose the region starts at A and ends at B. Okay. And then now, in order to get the region, to get the volume of the solid, so this is volume. Okay. The integrand should be the area. All right. But we are using cylinders, so what we'll do is what we'll use would be the surface area of a cylinder. And I'll tell you later why it is a surface area. But remember, the formula for the surface area of a cylinder is 2 pi radius times height. So we need to determine two things here. We need to determine the radius and the height of those cylindrical shells. It would be helpful if you can draw the cylindrical shells or how they look like. Well, you can draw the cylindrical shells by starting at the AOR, drawing a radius towards the end of the vertical strip. Okay, basically I'll have that. And then imagine the revolution happening. As you revolve the vertical strip about the axis of revolution, you're forming cylinders that look like this. Or at least half of the cylinder look like this. And if you consider a different vertical strip, then you will get another cylindrical shell, right? But this tells us something, that the solid is formed by infinitely many concentric cylindrical shells. So basically, you can imagine the solid being formed by considering cylindrical shells or cylinders that are empty inside or hollow inside that are very, very thin. And then we put one cylinder inside a bigger one, right? And we do this infinitely many number of times. We stack them very compactly so that we get a solid, all right? So that's why we take the summation, sort of, in quotation mark, the summation of the surface area of the cylinders because they make up the entire solid, right? And now we need to compute what is the formula for the surface area. It's 2 pi radius times height. But we need to measure what is the radius of the cylindrical shells. Well, if you look at the figure, the radius of the cylindrical shell is from here until there. Okay? Now, I hope you will remember this convention. Whenever measuring something from the y-axis to the right, that's always y units. Oh, sorry, that's always x units. Okay? And then whenever measuring something, because why did I draw the y-axis like that? The y-axis is here. And if you're measuring something from the y-axis towards the right, that's what I meant, towards the right, then that's going to be x units. On the other hand, if you are measuring something from the x-axis upward, that will always be y units. Okay? So in this particular case, my radius would be x units. Okay? And then the height would be the height of the vertical strip. This is the height, top minus bottom. Okay, and then this is the radius. And then we'll play around these conventions to exactly determine what's the radius and the height of our cylindrical shells. But I guess that's the gist of this method. So we need to imagine how the cylindrical shells look like and then compute their radii and their heights. Okay. Now let's look at a couple of examples to make this discussion more concrete. Let's go back to problem 15. We have the region R bounded on the first quadrant by y equals 8x, y equals x cubed, and then we look at several solids of revolution form by revolving the region R with respect to different axes of revolution. So we did this last time, but we use the disk or the washer method. So let's do it the other way around using cylindrical shells. Okay. Now let's do it for 15A. Let me just copy the region. Over here. Okay. So that's the region. Remember that the blue curve is y equals 8x, and then the red curve is y equals x cubed. Okay. And then we knew the points of intersection are the origin and 2 root 2 comma 16 root 2. Okay. And then the axis of revolution for 15A is what? For 15A, it's the x-axis. So we are revolving with respect to the x-axis. Okay. Now, in order to use cylindrical shells, the strip should be chosen parallel to the AOR. So strips are parallel to the AOR. That's always a requirement for the cylindrical shells method. Well, so the volume will require the use of horizontal strips because our axis of revolution is horizontal, okay? And horizontal strips involve the variable y, always. So you cannot simply say, I'm going to use cylindrical shells, but I will integrate with respect to x. The determination of the variable and the type of methods are dependent on the strips and their position relative to the axis of revolution, right? So again, here we're using horizontal strips. That's why I'm using dy. And those horizontal strips are parallel to the axis of revolution. So I'm going to use the cylindrical shells method. Okay. Now, since we are integrating with respect to y, I need the bounds for y. If we look at the y-axis, we see that the region started at y equals 0 and ended up at y equals 16 root 2. So those would be my bounds. Okay. And then the integrand, okay, inside the integral, will have 2 pi radius times height because we're using the methods of cylindrical shells. I'm going to put 2 pi right ahead in the integral. That's a constant. It's not a big issue there. Now let's determine the radius and the height, okay? Let's do the radius first. But again, it's helpful to draw how the cylinders look like, right? The radius of the cylinders will be coming from the axis of revolution towards the strip. And then if I will revolve the strip with respect to the axis of revolution, I'll get cylinders that look like this. Or at least this is half of the cylinders. Okay, those are this is how those cylindrical shells look like, right? So I usually want to simply draw the upper half, or yeah, half of the cylinder, so that the figure won't look very messy, because I'll base my measurements from this figure. But I hope you can imagine how the cylinders look like, right? So now I need the radius. Well, what's the radius of this cylinder? Well, the radius of the cylinder is this, okay? But how long is that? Remember here, I'm measuring it from the x-axis upward. And do you remember the convention I just laid down earlier? Whenever measuring something from the x-axis upward, that's automatically y units, right? And the question is, can I put y inside the integral? Yes, I can, because we are integrating with respect to the variable y. So that means the radius is equal to y. And then let's determine the height. Well, where is the height of the cylinder? Well, the height of the cylinder is this. Oops, it's this, right? That's the height of the cylinder. Okay. Now, how do we measure the height of that cylinder? Well, based on the figure, you should realize that that height is nothing more but the length of the horizontal strip. Okay. And then, do you remember how we measure the length of a horizontal strip? It's always right minus left. Okay. So the height is right minus left. Okay. Now, to get, we need the equations of the right and the left functions, but we are integrating with respect to y, so I need to solve for to write the equations in terms of the variable y. So the blue curve can be rewritten, or the equation of the blue curve can be rewritten as x equals y over 8. And that of the blue of the red curve can be rewritten as x equals cube root of y. Okay. And then again, the height of the cylinder, which is the length of the horizontal strip, is right minus left. Right minus left, so that's going to be red, cube root of y, minus blue, which is y over 8. And that would be the integral that will give you the volume of the solid using cylindrical shells. If you carry out the integration here, you should get, let me see my notes here. I computed it earlier. It's 4096 root 2 over 21 pi, which is basically the same value you will get if you integrated with respect to x instead. Okay, so these two methods are equivalent to each other, or at least their answer should be equal to each other. Though we use a different method and we use different types of strips. Okay, does that make sense? Oh, Faiza, how did I get 16 root 2 for the upper bound? Well, I guess last time we solved for the points of intersection. It's over here. I solved for the points of intersection because I knew that they will the region will stop at the second point of intersection. Okay. Now, if I do the solution, I will get x equals 0 and x equals plus or minus 2 root 2. So those are the x values of the points of intersection. And I knew here that the point of intersection that we are interested in has x component to root 2, right? But I'm looking for the y value. Well, you can plug in 2 root 2 into either 8x or x cubed. And you will get 16 root 2, right? I just decided to plug it into y equals 8x because it's easier to compute, so I get 16 root 2. But you'll get the same answer if you plug in into y equals x cubed. Okay? And that's a very important thing. That's why I usually start the solution by looking at the points of intersections first. But I just assumed that we had computed it earlier from previous time, so I just quoted it. Okay? All right. Let's try another one to see some variation over here. Let's do problem B. For problem B, we have the same region, but the axis of revolution now is the y-axis. Okay, axis of revolution is the y-axis. If we insist on using cylindrical shells, then the strips should be vertical, because we want the strips to be parallel to the axis of revolution, right? Now, since we're using vertical strips, we'll be integrating with respect to x. Then you should be careful and see if you need to split the integral up into two pieces or two or more pieces. But if you look at the vertical strip, you slide it to the left and to the right of the region. The blue function is always on top. The red function is always at the bottom. That signals we don't need to split the integral up. So we can do a one-shot integral for the volume of this solid, right? And that integration will go from the starting x value, which is 0, and then the ending x value, which is 2 root 2. So those would be our bounds for x, okay? And then remember cylindrical shells, we need the surface area to be the integrand, so it's going to be 2 pi radius times height. Now to find the radius and the height of the cylinder, let's draw the cylinders. So that's the radius. So my cylinders will look like this, right? That's how the cylindrical shells will look like. And then the radius of this cylindrical shell will be from here. Remember the convention that we had whenever you are measuring something from the y-axis towards the right, that's always y units. And that was the case here, right? So we are measuring something from the y-axis towards the right, that's always y units. Can y be, oh sorry, that's always not, it's already Friday, sorry about that guys. It's x units. Coming from the y-axis towards the right, that's always x units, okay? And the question is, can I put x into my integral? Yes, because I am integrating with respect to x. So the radius is x units. I can put that there. And then what's the height of the cylinder? Well, the height of the cylinder is basically this, right? That's the height of the cylinder. But the height of the cylinder, as we see in the picture, is the length of the vertical strip. Now we measure the vertical strip as using top minus bottom, right? And then remember that the equation of the blue curve is y equals 8x. And then the red curve has the equation y equals x cubed. And then when we do top minus bottom, it's going to be 8x minus x cubed. Okay. And then when you calculate this integral, you get 512 root 2 over 15 pi. I don't think the integration will be hard for you, so yeah, I'll leave the calculations to you. Because if I remember it right, the worksheet tells us to evaluate the integrals in 15a and 15b. Okay, any questions so far? Is it going good? Okay, I'll take that as a silence of type 1. Remember, type 1 means you understand everything, that you don't have any questions at all. I hope it's not silence of type 2. Remember, type 2 is you don't understand anything, so you cannot make up any sensible question. So I hope it's a type 1. But perhaps some of you are still trying to decipher or to digest it. Okay, it was a little bit too fast. So let's look at more examples. Then I'll work at it a little bit slower. Okay. Now let's do problem C. Again, for now, for problem C, we still have the same region, but the axis of revolution is x equals 2 root 2. Okay. Let's see the picture. Well, the axis of revolution is x equals 2 root 2. So that's how the axis of revolution is situated, okay? And then let's compute the volume. If we want to use cylindrical shells, again, we use strips that are parallel to the axis of revolution. The axis of revolution is vertical, so I will use vertical strips also. Okay, and since I'm using vertical strips, the variable for the integral will be x. Okay, and then look at the vertical strip that I drew. If I will move it to the left or to the right, the top function is always the blue one and the bottom function is always the red one. That tells me I don't need to split the integral up into two pieces. I can do a one-shot integral for the volume. And then the integration will be carried out from the starting point of the region with respect to the x-axis. So it started at x equals 0 and will end at 2 root 2. Again, the bounds will be the bounds for the region. So regardless of where the axis of revolution is, the bounds will always be the starting x value and the ending x value of the shaded region, regardless of where the axis of revolution is. The same thing goes for y, okay? So now I know that the bounds would be from 0 to 2 root 2, okay? And then since we are using cylindrical shells, the integral will be 2 pi radius times height. So I'll put the 2 pi over here. And then I need to determine what is the radius and what's the height of the cylinders. Again, it's much easier to determine the radius and the height of the cylinder by drawing the cylinders themselves, or at least one cylinder. So from the AOR towards the end of the strip, that would be the radius. Then if I do the revolution, I'll get a cylinder that looks like this. Or this is half of the cylinder. Okay. And then now I have an idea of how the cylinder look like, right? How the cylinder looks like. Then I can determine what is the radius and what's the height. Perhaps I'll start with the height first because the height is easier. Because here the height would be just this length, right? The cylinder is vertical, so the height will be that. But if you notice that the height is simply the length of the vertical strip, right? So the height would be top minus bottom. Remember the top function is, well, I should have copied it earlier. But anyway, the blue line is y equals 8x. The red line is y equals x cubed. So top minus bottom. So that's going to be 8x minus x cubed, right? And that's the height of our cylindrical shells. Okay. Now, calculating the radius for this one would be a little bit trickier than before. Well, where is the radius? The radius is over here, right? Or let me just highlight that using a different color. Okay. Okay, the radius is that red strip over there. Okay. So the radius, I'll just project it here, is this from here until here. That's the radius we are looking for, right? But any guess how long that radius would be? Looking at the figure. Any guess? Come on, guys. It's free to guess. No penalty for wrong guesses. But I hope you all agree that that's the radius that I need to measure, right? That's the radius of the cylinders. No guesses? Jocelyn, you guessed x minus 2 root 2. You're almost there. Okay. Just a little adjustment. Actually, here, let's see. From here, from the x-axis, from the y-axis until here, that's 2 root 2 units, right? But from here until here, that is x units, right? Because I mentioned whenever measuring something from the y-axis towards the right, that's always x units. So based on this figure, what's the radius? I hope you guys can visualize it. Jocelyn, you want to adjust your answer? Uh-huh. Christina, you're correct. So that's going to be 2 root 2 minus x. Yeah, Jocelyn, you're correct. So you see the idea here. It's much easier to set up, to find the radius and the height if you have an idea how the cylinders look like. All right. And remember the convention. From the y-axis towards the right, x units. From the x-axis upward, that's y units. Okay? All right, any clarificatory question about this? Okay, none? Is it clear? Okay, let's try another one then. Let's try question D. For question D, we have the same region, but the axis of revolution is y equals -1. So the axis of revolution could be here. Y equals -1. That's the axis of revolution. Again, here we have y equals 8x, and then we have y equals x cubed. Okay. Now we will use cylindrical shells method here. We need to decide what type of integral to use. Well, the axis of revolution is horizontal. Cylindrical shells method requires parallel strips to the AOR. So that means we will use horizontal strips. And horizontal strips always go with a variable y. So we integrate with respect to y. Okay? And then if you imagine the horizontal strip being slid up and down the region, the red curve is always on the right, the blue curve is always on the left, so that means we don't need to split the integral up into pieces, okay? So we can do a one-shot integral over here, and the integration should be carried out from the starting y value until the ending y value, okay? The starting y value for the region is 0, and the ending y value is 16 root 2. Okay? And then we're using cylindrical shells, so that means the integrand should be the surface area of the cylinders. So we need a 2 pi radius times height. Okay? Now to find the radius and the height, I'll draw the cylinder, or at least half of the cylinder. So from the AOR towards the strip, that's the radius, and then the cylinder will look like this. Or half of the cylinder will look like this. Okay? Now let's compute the radius and the height of the cylinder. I guess it's easier to find the height of the cylinder here because the height of the cylinder is this length, right? That's the height of the cylinder because the cylinders are horizontal here. But nevertheless, that's going to be the height. But the height is the length of the horizontal strip. And we said that horizontal strips are measured using the formula right function minus left function. Okay. Now, but notice that our variable here is y. So I need the functions to be expressed in terms of y. So that means I need to rewrite my function here as x equals y over 8. And then this should be rewritten as x equals cube root of y. Okay. And then if I do right minus left, I will get right is the blue curve. It's the red curve, so that will be cube root of y minus the left curve, which is y over 8. So that's the height of the strip. Okay. So let me just put that in our integral. So we have cube root of y minus y over 8. That's the height. Now let's look at the radius, which could be a little bit tricky. But it will always help if you draw the cylinder. So this is the radius, right? How long do you think is that radius? Any idea? Any guesses? Perhaps when I'm waiting for your guesses, I should play something on the background just to make it more interesting. Faiza, try again, but you're near. Okay, Jocelyn, you're correct. It is y plus 1. Why do we have y plus 1? Well, remember, I mentioned earlier, measuring something from the x-axis upward, that's going to be y units. So this guy would be y units, right? But from here, from the AOR towards the x-axis, that is 1 unit, right? Because this is -1, this is 0, from 0 to -1, that is 1 unit. So in all, this radius would be y plus 1 unit. So that's why the height, the radius of the cylinder is y plus 1. Okay, I hope that's clear. And you see how helpful the picture was in determining the radius and the height of the cylinder. So that's why I suggest every time you work problems like this, you always sketch the figure. Well, you can find some formulas for this, but I always think that understanding the process is much better than simply memorizing the formulas. And personally, for me, memorizing formulas is very difficult. It's hard for me to memorize something. So that's why until now, even if I had been teaching this topic for more than 10 years now, I always go back to the figures. So I don't want to memorize what's the formula for the radius and for the height, but I analyze the figure themselves. Okay. Any questions? Well, in the worksheet, there are 3 more questions, 16, 17, and 18. Though we solved them last time using the disk or the washer method, you can also set up the integral using cylindrical shells. But perhaps I'll skip that for now and go over the questions that were sent earlier. But don't worry, I will include the solutions to 16, 17, and 18 using the cylindrical shells method in the annotated version of the worksheet that I will upload later in the day. And I guess that will complete the worksheet. So hopefully next time we'll have worksheet number 4, but at least you will have a complete solution for worksheet number 3. But again, I guess worksheet number 3 doesn't have an explicit instruction to use a certain method. So you are free to choose whether you use disk or cylindrical shells method. So it's up to you which you think is easier. For me, the prime criterion in choosing what type of strip to use is whether or not I need to split the integral up into several pieces. If one strip will require splitting the integral, then I'll choose the other type of strip. Okay. But another thing is that you should also look at which one would be easier to integrate. So sometimes the setup might be easy for one strip, but integrating it would be a different ball game. It might be more difficult, right? But fortunately for most of this worksheet, we are just required to set up the integral. So I guess setting them up both would be fine, and that will give you an insight in using those 2 methods interchangeably. Okay. Now, if that's good, let me go to Jocelyn's question earlier. So she sent this problem. I guess this is problem 10 from your electronic homework. By the way, I will not include the solution to this in the uploaded version of the worksheet. So just pay attention to the discussion here. I won't include it so that you will be forced to write your own solution. But of course, this is part of the recording, so you can still rewatch it. But the point is, I want you to understand the process here. Okay. Now, for her question, okay, so this is a method of cross sections. Okay, so the base of the solid is the region bounded by x equals y squared and x plus 2y squared equals 3. And then the cross sections are semicircles. that are perpendicular to the x-axis. So, and then she needs to find, yeah, we need to find the volume of this solid. Well, it would be good to have a picture of the shaded region. I'll start with x equals y squared. That's a parabola opening to the right with vertex at the origin. So that's y equals, oh, sorry. This is x equals y squared, okay? And then the other one is this. I can rewrite it as x equals 3 minus 2y squared. It's a parabola with vertex at y equals 0. When y is equal to 0, x is equal to 3. Then when x is plus or minus 1, oh, sorry, when y is plus or minus 1, x would be equal to 1. Though I know that they will intersect there. Oops. Because when x is equal to 1, then y is equal to plus or minus 1 also for the first parabola, right? So that saved us a little, that saved us some time because we know that the intersection happens at x equals 1, okay? And then now so this is the shaded region. And then we were told that the cross sections are semicircles which are perpendicular to the x-axis. So a typical cross section would be like this. So this is perpendicular to the x-axis, and this would be a semicircle. Okay. But if you draw this cross section here, somewhere towards the right, you will also get a semicircle, but you see the difference in the functions involved because here in the in the cross section here, I have the right function on top, the red curve on top and the red curve also at the bottom. So here I have the blue curve on top and the blue curve in the bottom. So that means I need to divide the integral up into two pieces, okay? But luckily, I know where to divide the integral up or to split the integral because I know the point of intersection happened when x is equal to 1, right? To the left of x equals 1, it's red versus red. On the right of x equals 1, it's blue versus blue. That's why I need to split the integral up into two pieces, okay? Now, the volume will be given by two integrals, and then we'll sum them up. And since we are using vertical strips here, because the cross sections are perpendicular to the x-axis, so the variable of integration here would be x. And then the first integral will be an integral from 0 to 1, because on the interval 0 to 1, it's red versus red. But on the interval 1 to 3, it's blue versus blue, okay? Now, we are integrating with respect to x. So that means what will happen here is that all the functions should be expressed in terms of the variable x. So if I begin with the red curve, I can solve for y in terms of x and get y equals plus or minus root of x. That means the upper red curve is root of x, and the lower curve is y equals negative root of x. Okay. But what are the cross sections? The cross sections are semicircles. And remember, the formula for the area of a semicircle is 1/2 the area of a circle. Okay, 1/2 radius squared. But what is the radius? The radius is half of the length of the vertical strip. So here the vertical strip, actually the length of the vertical strip is the diameter, right? And this would be top minus bottom, okay? And what is the top minus bottom? Well, we said that the top curve is root x. The bottom curve is negative root x, so we'll have negative root x. So that means the diameter is twice the root of x. Okay. But we're looking for the radius. So radius would be half the diameter. So it would be root x. So basically this would be 1/2 pi times root of x quantity squared. So the integrand over the interval 0 to 1 would be 1/2 pi x. All right. And then if you do the same thing for the blue curve, I mean, you apply the same principle. You solve for y in terms of x. So we see that x is equal to 3 minus 2y squared. Solve for x in terms of y will tell us that what? X minus 3 is equal to negative 2y squared. Divide both sides by negative 2 equals y squared. So that means y is equal to plus or minus the root of 3 minus x over 2. Okay, so the top curve is the square root of 3 minus x over 2. The bottom blue curve is negative root of 3 minus x. You take the diameter. So the diameter for the blue curve is twice of root of 3 minus x over 2 using the same principle as we used in the red curve. And we solve for the radius. The radius would be just half of the diameter. So it would be root of 3 minus x over 2. Then plug that into the integral. So remember our integrand would be the area of the semicircle. It's 1/2 pi radius squared, but radius squared would be root of 3 minus x over 2. Oh, I will square it, so the square root will be gone. Okay? And then you evaluate these two integrals separately and then add them up, then you get the area, or you get the volume of the solid. Let me just look at the problem again. Yeah, this problem asks for the volume, so you need to give me the exact numbers. So you need to evaluate these two integrals up, then add them to each other. That will give you the volume. All right. I hope that made sense. Any clarificatory question on that? All right, you're welcome, Jocelyn. I still have 2 minutes. Any other question? I remember Lucas sending a question. Can you send me the screenshot, Lucas, of problem 10? And then I can stay until 12:55 for that question. Or anybody has a copy of homework 10? Oh, that's actually problem 10. Oh, okay, that's good. That saves me time. Any other question? Yeah, I said I am not uploading the solution to problem 10 into the annotated worksheets, but I'm keeping it on the screen. So that's the advantage of attending the labs. So you get this perks of asking questions and seeing solutions to perhaps some of the problems that you need to submit. But I hope you guys just don't copy the solution. You organize it your way. You try to recreate the solution because you might get a perfect score for this problem without understanding it. But during the exams, I will not be there to help you. So I hope you understand the process and try to recreate the solution on your own. Okay. So if there are no other questions, then let's call it a day. I hope you guys had a good week and hoping for a good weekend for everybody. So thank you guys for coming. Let's see each other again on Monday. Goodbye.